So welcome everybody. My name is Robert Schilling. I'm a PhD candidate at Graz University of Technology under the supervision of Professor Stefan Mangard. And today I'm talking about the secure software execution of basically general purpose software, not particular about crypto. All right, let's start. So I think I don't have to argue with anyone that it doesn't make any sense to write the best software we possibly can, as long as we don't have functioning hardware. When we look at the modern computing landscape we nowadays have, that's actually a problem, because most of the devices we use, like mobile phones, notebooks, smartwatches, and so on, they are designed to be carried around. They are designed to be mobile, and they operate in environments which we don't really control. We also have the same situation in cloud computing. We are using servers which you don't know where they are located, who is operating them, who is operating the environment for them. And what happens as a result is that as soon as you change some of these operating conditions, these devices may stop working, may start behave strangely. And this is actually what the fault attacks are about. So we change the operating conditions of our devices, we mess up with the operating voltage, with the clock signal, and so on. Or we maybe use a laser to inject light pulses onto the chip. And what happens with these faults is quite simple. The processor starts to behave strangely. Maybe some data is changed, maybe some pointers are changing. They're pointing to a different memory location, for example. Or it can also modify the control flow of the program. For example, the branch target may jump to a different location, or a conditional branch is taken, which it should not, or so on. And this is also observed in the industry. For example, the Xbox 360 was attacked by a hardware attack, where a glitch on the reset line was able to bypass a signature verification algorithm of the firmware, and we were able to execute arbitrary software on that device. So these are fault attacks which require physical access. So you need to have access to inject a glitch, for example. So this setting is true for many applications. But very recent research shows that fault attacks can also be injected via software, but there's no physical access. One prominent example for that is, for example, the Rowhammer effect, where accessing the memory or causes neighboring bit flips, neighboring memory cells to flip and inject faults. This attack was then extended to also be exploited remotely via the network interface with NetHammer and Throwhammer. And very recent work like Blunderbolt, Oldjock, and Clockstrew were able to inject classic fault attacks like power glitches or clock glitches via software into the device. Yeah, so with this new attack methodologies, there's no need for expensive devices anymore. So you don't need to have a laser and so on. And you also don't need to have physical access to the device. So fault attacks now also threaten ordinary commodity systems, and the attack surface is really increased here. Okay, so what can we do here? What can we do to defend against these fault attacks? The solution is quite simple. We basically add redundancy. We want to add redundancy everywhere. But on a more serious note, what we usually do here is we add modular redundancy, spatial redundancy. We duplicate our processor and then continuously check if both executions deliver the same result. And if not, then we decide on reporting a failure, for example. The problem here is that when you need to duplicate everything, it's really expensive. Think about all the caches, the bus systems, maybe also the RAM. So in general, that is too expensive. And on the other hand, it's also not that flexible. So you cannot decide on sections of a code which maybe require more protection, others which are not so important. Software countermeasures, on the other hand, they obviously have more flexibility. So you can control how much redundancy you want to have. But software countermeasures still rely on a functioning hardware to some degree. And also usually they have very strong assumptions on the fault model. For example, they only consider an instruction skip model. So the attacker is only able to skip one instruction, but what about the data then? So what you really need is we want to have a more fine granular methods on protecting the software execution of CPUs. Yeah, so let's start with some first work we did. And that is about control flow integrity. So control flow integrity in the context of faults is very similar to the control flow integrity you maybe know from software attacks. However, when it comes to fault attacks, we want to enforce CFI on a much finer granularity. In the best case, we want to enforce the correct execution of all instructions. So we want to protect the instruction sequence. Yeah. So CFI exists on different levels of granularity. So for software attacks, we have CFI for indirect function calls. Here, the attacker model is, for example, overwriting indirect function calls via stack corruption. So, but this is too coarse grained for fault attacks. At the best level, we want to have CFI on instruction level. So really, we want to enforce the correct sequence of every instruction. But to deal with that, it requires very intrusive hardware changes to deal with the performance penalty these schemes have. So when you want to protect commodity devices or devices where you cannot change the hardware, this is simply not possible because the software overhead would be too large. As a trade-off, there is also there's a basic block level granularity. So with basic block level CFI, you ensure that the connection of all basic blocks in your program is genuine. And to do that, you determine the control flow at compile time and then use some mechanism to enforce that at runtime. A nice thing is that the overheads for these schemes, they are suitable for pure software design, so you can also protect commodity devices with that. Okay, so we developed a scheme for basic block level CFI for ARM devices. Especially, we are exploiting a new feature called ARM pointer authentication for that. So ARM pointer authentication is a new feature of very recent ARM devices and is developed to cryptographically sign a pointer. So it computes a MAC over the pointer and then stores that MAC within the pointer in the upper bits of the pointer. So it reduces the address space here. And it's originally designed to provide data integrity for special pointers like code pointers and return addresses to ensure those are not modified by software attacker. So they were originally developed for a very coarse-grained software CFI scheme. But we use that feature to build a fine granular basic block level CFI scheme. Essentially, what we are doing is that we take this pack feature, which has dedicated instructions, and we use that to update a global CFI state at the beginning of every basic block. So we essentially compute a MAC over the sequence of executed basic blocks. And that at certain positions in the program, we compare that MAC with the expected MAC at this location. Yeah, the nice thing is that this does not require any hardware changes. So we simply use the existing hardware we get from ARM. We also support different checking granularities in the sense of we can verify the state of the CFI at basic block level, at function end level, or at the end of the program. This, of course, has different impacts on the security and on the performance. Yeah, so this is a pure software design with no hardware changes. All right. Of course, you do not want to write code for that manually. So we developed a custom LLVM-based toolchain that can compile arbitrary programs instruments them, and inserts the necessary CFI checks and patching values at the basic blocks. And we also can configure the toolchain for different checking policies as mentioned before. We evaluated the design based on spec. Spec is a widely used benchmark which has large programs like GCC or JPEG conversions within. So these are fairly large programs. And on that, we see overheads between 50 and 100% in terms of code and around 30 to 100% in terms of runtime. This depends on the used checking policy. So if there's only a single check at the end of the program, then we are of course at the lower end of this ranges. And if we are doing a basic block level checks, then we are on the upper hand. The intermediate security policy, where we check at every end of the function, is interestingly more towards the lower end of these ranges, and therefore is quite nice to be used. All right. So with that, let's come to the second part. This is where we want to protect conditional branches. This is the point where the data meets the control flow. This happens for these conditional branches. So for CFI, we restrict the program execution to only valid execution traces, which must follow a statically determined control flow graph. So this control flow graph basically determines the correct execution. However, for conditional branches, both branch targets are valid executions in terms of the control flow graph. So if an attacker bypasses a conditional branch to jump, for example, to the true case instead of the false, this cannot be detected with CFI because both targets are valid. However, an interesting observation, conditional branches are used for quite some sensitive code. So they're used, for example, for password checks, for signature verification, and other privilege checks. So we really need some extra protection for those operations. So how can so let's look at a simple conditional branch. So the conditional branch is a combination of a comparison and then the actual branch depending on the result of the comparison. So when we look at this, an attacker has different possibilities to attack this operation. For example, he can attack the input data. He can modify that and therefore cause the conditional branch to jump to the other target. We also can attack the comparison operation itself or the result of the condition value to bypass the branch or change it, or the attacker can modify the branch itself. So in order to have a really secure conditional branch, we need to mitigate all these attack vectors to be secure. So what did we do? So what we do is, in the first step, we add redundancy to the data. So we encode data to different representation such that we have some bits in redundancy there. One example for that we use here is so-called EN codes, which are arithmetic codes. And the nice thing about that type of code is that these support arithmetic operation directly in the encoded domain. So you do not need to decode the data to perform an addition, for example. You can do that in the encoded domain. So the input data is now encoded. And what we do is we develop now an encoded comparison operation that instead of computing a 1-bit condition value, it computes a redundant n-bit condition value. So it computes an n-bit symbol for the true value and another n-bit symbol for the false value. But how can we now branch based on that redundant condition value? Well, the first thing we do now is we take an ordinary conditional branch again. We compare that to the expected condition symbol and then branch depending on that. However, this does not gain any security because again, there is this intermediate 1-bit signal an attacker could modify with. So what do we do? So basically, we perform one trick. So when doing the comparison operation, we already know how to branch ahead because when we compute that condition value, for example, a true case, then we already know we need to jump to the true case. And if we computed the false value, we know to jump to the false path of the code. So this condition value is already a branch target dependent value. So the true symbol maps to the true path of the code, and the false value maps to the false path of the code. And what we do is then at the branch target, we take this value and modify our CFI state with that. And this means that only if we did the comparison correctly and we jumped correctly, this CFI update modifies the state correctly, and we have a correct CFI state. Otherwise, if we jumped to the wrong path, this CFI state would be corrupted, and we would have a CFI error. So with this work, we closed some gap between data protection and CFI. We developed a generic approach. So the generic approach is that we link a redundant condition value to the CFI state. This is generic in the sense that it doesn't depend on the actual used data encoding scheme. So you only have to develop an encoding comparison operation for that. We integrated that work into an ARM-based CFI scheme, as well to a custom RISC-V processor where we have instruction granular CFI protection. We also have an LLVM toolchain for that. So this toolchain basically identifies conditional branches and then determines the tree or the related data to that conditional branches, encodes that to the AN code domain, replaces all operations to the encoded operations, and also replaces the comparison with an encoded comparison. In the evaluation, we see that this is the overheads are on par with comparison trees, where we simply replicate the comparison many times. However, with our scheme, we also have data protection, so we get the protection of the data at the same costs. All right, so with that, let me come to the last part. I'm talking about memory accesses. So memory accesses are basically everywhere and are, besides the computation, the largest amount of instructions in a program. However, with that type of operations, many things can go wrong again. So let's look at that simple example here. So we have a pointer pointing to some location in memory. And then when we want to perform a memory access based on that pointer, maybe a fault attack occurs. The fault attack maybe manipulate our pointer. It can redirect the location, for example, to point to some secret value. And then the subsequent memory access will read that secret for you. However, this is not the only attack vector. Second attack vector is the memory access itself. So even though the pointer might be correct, a fault attack directly during the memory access could redirect the memory access again to our secret. So in order to protect memory accesses, both of these attack vectors need to be protected. So let's start with the first one. Let's start with the pointer. So in order to secure that, we need to, again, add redundancy to the pointer. So this allows us to detect any unwanted manipulations on it. So what we do here is we use an encoding scheme called multi-residual codes and encode that encode the pointer with that. So this encoding scheme has several advantages. The first one is that this code is separable, meaning that you basically add the redundancy bits to the pointer, and the functional value, the original value of the pointer, is always accessible. So there is no expensive decoding step needed for accessing the original value of the pointer. And this is very important because for the actual memory access, you need that original value. On the other hand, multi-residual codes are also arithmetic codes. So they also support arithmetic operations directly in the encoded domain. So again, you don't need to decode the data in order to perform, for example, a pointer increment. You can do that directly in the encoded domain. Yeah, but there's still a question where to store that redundancy efficiently. So there's there are different possibilities for that. For example, you could use a parallel register file for the redundancy information, or if you don't want to waste that much of hardware, you can, for example, use a pair of regular registers. The first one stores the original pointer, and the second register stores the redundancy information of it. But what we use is we take our pointer and reduce its address space. And then at the upper bits of the pointer, which are not used anymore, we store our redundancy information, in this case, our residues. So you see that in this figure, the upper bit, the upper part of the pointer stores this redundancy information. So here we, on a 64-bit platform, you can do that easily, and it's also done in other work. And with that, you don't have any overheads in terms of hardware, or you don't add any overhead to the register pressure, for example. All right, so pointers are not protected, but the memory access is still unprotected. So in order to protect the actual memory access, we need to establish a link between the redundant pointer we have in the register and the data. So essentially what we perform is we perform some kind of scrambling. We scramble the data when writing it to the memory and unscramble it and reading it back. And for this, we use the redundant pointer as our scrambling key. And only if we read from the correct location in memory, we are using the correct pointer, so the pointer is not modified. This unscrambling operation succeeds, and you get back our original data. In any other case, if we, for example, have a fault attack and read from the wrong location in memory, then this unscramble operation will lead to garbage for the right data. And if you have some kind of data encoding scheme on our payload data, which is needed anyways for secure applications, we can detect those wrong memory accesses. So in a nutshell, we're translating here addressing errors, wrong memory accesses, to data errors, which we eventually can detect in software. We implemented also a prototype here based on RISC-V, based on the RISC core of Pulp, which we extended to 64-bit. We integrated a dedicated ALU for multi-residue operations. So we added new operations for that, like pointer increments or additions and so on. And we also added new instructions for those linked memory accesses. We also developed a custom LLM toolchain. So this allows us basically to encode all data pointers, all pointer arithmetic to this multi-residue domain, and then replaces all memory accesses with those scrambling memory accesses I talked before. The nice thing is that with that, we don't have that much of performance penalty. So with the hardware support of the LU, we have runtime overhead and code overhead of less than 10%, which is quite reasonable for our first research prototype. So with that, let me shortly conclude that talk. So with all the modern use cases we have, the threat of fault attacks has evolved. So it evolved from this classical fault attack setting on very small devices, where you have physical access, up to now commodity devices, where you can do physical attacks, but also nowadays software-based fault attacks. And it really requires different countermeasures to protect against different scenarios. Unfortunately, there is no silver bullet solution to protect against all attacks at once. Instead, we need to have different layers of defensive to protect against certain attacks. And what we also see is that the support of toolchains is quite important, because nobody wants to manually annotate existing source code, protect them, harden them against fault attacks. Instead, this must be done automatically by compiling them and inserting the countermeasures there. So, all right, with that, I'm now at the end of this talk, and I'm happy to take any questions before the lunch break.